Hey guys, so we're going to talk about enzymes today. Don't mind my cat meowing. This is going to be a lengthy video, so if anytime you need to take a break, go ahead and take a break. I think I'm going to use about 3 pages, so you can do this. All right, find your next page, just title it Enzymes. So you should have done your reading. You should have attempted to do your online virtual lab. If you haven't done any of that, that's fine. Watch this video. If you need to read, go read. And then make sure you do your online lab before Friday at midnight. That's when it's due. So enzymes are essentially proteins. And if you remember when we talked about proteins, remember we've always kind of said that they have 4 stages of folding. So there's the primary structure, secondary, tertiary, and then the optional quaternary. So because proteins are folded so specifically based on their amino acid sequence, we say that for proteins, their structure defines their function. So structure defines function. Meaning, how the protein is folded defines the function that that protein can do. If you fold your protein differently, it'll give you a different function. Because enzymes are proteins, this holds true. We can change the function of an enzyme by causing it to fold differently. So enzymes are catalysts. And a catalyst is anything that will speed up a chemical reaction. So what enzymes do is they're going to cause reactions to occur at a faster rate, so they speed up chemical reactions. I'm going to denote reactions are XNS, so that means reactions. And the way that they speed up a chemical reaction is by decreasing the amount of energy it requires to get your reactants to their transition state, or decreasing the activation energy, which is denoted E sub A. So let's draw what this would look like. So have your axes. Over here on your x-axis, you're going to have progress of reaction, so it'll be time. Okay, on your y-axis, you're going to have free energy. Awesome. So if you remember, we're just going to draw a regular exergonic reaction. So in a regular exergonic reaction, the energy of the reactants is higher than the energy of the products. And so when our reactants become our products, you have a negative delta G. So you have final minus initial. So you have a low value subtracting a higher value. That gives you a negative value. So if you remember the value, so reactant energy, final energy, that difference, that's our delta G. And for exergonic reactions, that's a negative value. If you remember the amount of energy it takes to reach this peak, this is called the transition state. So let's just label that transition state. The transition state are when the molecules are the most unstable. So we're taking our reactants, we're adding an amount of energy, and we're breaking those bonds. So you put energy in to break the bonds, and then as the new bonds form, we have this release of energy. So the transition state, the energy it takes to reach that peak from the energy of your reactants, that's called your activation energy, or EA. This should all be review. So let's just make a little key. So everything I just drew in purple, that's going to be the progress of a reaction without an enzyme, or in the absence of an enzyme. An enzyme will speed up a chemical reaction by decreasing the activation energy. The energy of the reactants, the energy of the products stays the same. So we're not changing the molecules. We're just altering how much energy is required to run the reaction. So it appears to have a smaller peak. So now our activation energy is from this peak to the energy of our reactants, which is the same, And this is our new activation energy with an enzyme. So everything in red I just drew is with our enzyme. So enzymes will make a reaction occur faster because the reaction now requires less energy for the reactants to reach their transition state than it would without an enzyme. So the delta G doesn't change. We haven't changed the energy of our products and reactants. So our delta G is still negative here, and it's going to be the same amount. So the only value changing is your activation energy. The activation energy, like how much energy is needed, it's proportional to how strong your bonds are. Oh, here comes the cat. Ching, can you go somewhere? Bye. So the activation energy is proportional to the difficulty of breaking the bonds. So from one reaction to another reaction, the activation energy amount is going to be different depending on how strong the bonds are in the reactants. So an enzyme decreases the activation energy because it's making the bonds easier to break in the reactants. So let's talk about how. So that's right, how. That's where we're going to go to next. So the how includes bonding. So let's use the example from your lab. So in your lab, you had an enzyme, and that enzyme was called lactase. And lactase has a really specific shape. So I'm just going to draw it like a little Pac-Man. So this is lactase. Also, this is how enzymes work in general. So I'm just going to label our little Pac-Man E for enzyme. So enzymes are proteins. They have a really specific shape. So like this enzyme is shaped really specifically like this. There will be reactants that could possibly interact with this lactase. So there might be reactants shaped like this, there might be reactants shaped like this in the environment, and there might be some shaped like this. So all these reactants will be in the same area as your enzyme. So these are called substrates. Substrates are the molecules that bind with enzymes. So if it's a chemical reaction, these are also the reactants. Okay. And it's a lock and a key model. So the really specific tertiary structure of this enzyme has given it this really specifically shaped groove. And this groove is called the active site. Okay. And they're really specific. So if I have a substrate shaped like this, it's not able to bind to my active site because their shapes don't match. They don't have an affinity for each other. Same thing with this substrate. They don't have an affinity for each other because their shapes don't match. But if you look here, this substrate is perfectly matched to this active site. So they have an affinity to bond. It's a weak interaction, and they will bond. And that will give you a complex. So when a substrate bonds to its reactant, that made no sense. When an enzyme bonds to its substrate, like so, it'll just look like this. So your little substrate is now bound to the active site. So this is called an enzyme substrate complex, because it's a complex of your enzyme and your substrate. Once those have bound, the enzyme is going to kind of stretch and pull on those bonds so it reaches that transition state quicker, and then the enzyme will release its products. So the enzyme is still here, it still has its original shape, but it's going to release your products, and they're going to be different from what you put in. Okay, so for example, in your lab, you had the enzyme lactase, and your substrate was lactose, which is milk sugar. So lactose binds, you have this enzyme substrate complex, and the enzyme causes the release of two products. You release a molecule of glucose, so we're going to draw kind of smaller triangles, and a molecule of galactose, because lactose is a disaccharide, so it's broken down into its two monosaccharides. Okay, so like this is what happens in our guts when we eat dairy products. When we eat dairy products, well, in the case of like people who are lactose intolerant, we also take tablets that are lactase. And then in our guts, the lactase will break down the lactose into glucose and galactose. In the case of people who are not lactose intolerant, the bacteria in your guts produce lactase for you, and then that lactase will take care of the lactose you ingest, because we cannot digest lactose. So that's why people who are lactose intolerant, if you eat lactose, it tends to make you feel sick because you can't digest it. All right, so we have our substrates, lactose, example, binding to enzyme, our complex, and then our products are being released. So over here in this darker purple, I was showing our products. So it's all the same components of a chemical reaction. It's just kind of showing how. So the reason that I've been talking about this lock and key is there's something called specificity, and we're going to kind of zoom in on this diagram right here. So just kind of make your little zoom in lines. And what we're going to talk about is we're going to talk about the specificity of our enzymes. Specificity, meaning why do they have this lock and key model? All right, so we're going to draw our enzyme again. We're going to draw it just a little bigger. Okay. So the way we're drawing it, it's really globular. So kind of just imagine in your head that this is a protein that's been alpha beta pleated. It has beta pleated alpha helices, and then it's been kind of like globularized. So you can kind of imagine that all the R groups that are hydrophobic are kind of here in the core. All the I groups that are hydrophilic are kind of out here. Your acids, your bases are paired up. So there's really specific parts of our enzyme. This part is called the active site. And the active site is just a pocket or a groove where the substrate binds. And it's typically on the surface of your enzyme. You want it on the surface because then substrates in the environment can access it. So it's the pocket or groove where substrates bind. Okay. All the rest of this enzyme is all for framework. So everything else, all the other R groups are all providing framework for the active site. So they're kind of maintaining the structure of your active site, but they're also regulating the shape of your active site. When the substrate binds to this enzyme, remember we've talked about this thing we know. Whenever you bind or remove a molecule from a protein, the protein will change shape. So there's this really special phenomenon that occurs. It's called induced fit. So when a substrate binds to our enzyme, this whole protein is going to change shape in such a way that it kind of takes in or hugs your substrate. It's kind of like giving a hug. So when you kind of like approach to give a hug, your like arms are open and you're ready to hug. And then once the person is kind of in your vicinity, then you kind of change and you wrap your arms around the person. That's what an enzyme does. So an enzyme, when it has a substrate bound to it, its active site kind of changes shape. So I'm going to kind of draw it so like it would kind of hug or encompass our substrate here. So your substrate kind of gets encapsulated almost by the enzyme. This phenomenon where the enzyme changes shape to kind of surround and engulf the substrate is called induced fit. Where the enzyme and substrate are induced or caused to fit with each other because they bind with each other. Okay, so we have our enzyme here, and then you have your substrate here. And when they bind, it leads to induced fit. This is kind of like I said, giving a hug, but like think about being hugged so tight that your bones start to break. It's kind of what an enzyme is doing to its substrate. So induced fit is when there's a change in, so delta, change in shape of the enzyme, when the substrate binds. And what that does is now we've enhanced the enzyme's ability to speed up this reaction. So what the induced fit will do is it enhances their enzyme. So it enhances its ability to catalyze a reaction. And if you remember, we catalyze it by decreasing our activation energy. So we have to decrease the difficulty of breaking the bonds. That's what induced fit does. It kind of surrounds the substrate, and what it's doing is it's kind of applying pressure and strain. So that induced fit increases pressure on your substrate, but it's also distorting the bonds because it's stretching them apart or pressing them. So we're having increased pressure, but we're also stretching our bonds and pulling them, which makes them, which causes their activation energy to go down, because now when you apply this like stretching to the bonds, you only need a little bit more energy, activation energy, to actually break that bond. Versus when there's no enzyme, there's no real stretching, there's no strain, it's just the bond. So you need to add in this much more energy to further break that bond versus just a little bit more energy to break that bond. I always compare it to Of Mice and Men with Lenny and the puppies. So like enzyme is Lenny, the substrate is the puppies, right? And so he like grabs the puppies and then he accidentally squeezes them too hard, breaks them apart, and releases their products. That was really morbid, but that's the example I use every year. All right, next thing we're gonna talk about, so I'm gonna flip because I'm out of room. We're gonna talk about things that can influence the rates of our chemical reactions or our catalyzed reactions. So this will be rates of catalyzed reactions. And your lab dealt with two of them. It dealt with substrate concentration and pH. So let's just like review just the substrate one. So general rule, as you increase, can you see that color? Increase the concentration of your substrate or your reactants. That's gonna lead to an increase in your rate of reaction. But not forever. It's gonna only go to a point. So we're gonna have increasing substrate will cause an increased rate of reaction until the enzymes are saturated. So if we were to look at this graphically, your graph would plateau, right? So if on our x-axis we have substrate concentration, we're just going to keep adding more substrate, and then on our y-axis we had rate of reaction. It's going to hit a plateau. So we're going to follow our rule. So as we increase substrate, we increase rate of reaction. And then you're gonna hit a point where you've reached your maximum rate and you're just gonna plateau. The reason that we increase is because when you increase the amount of substrate, you have more molecules that can now access your enzymes. So it's gonna make your reaction go faster. But eventually you're gonna run out of enzymes. They're reusable, but you're only gonna have so many unless you add more. So we hit this plateau because all the enzymes we have are being accessed, and so there's no more enzymes available to break down more substrate. So your rate of reaction will plateau. It won't decrease, it'll just stay at a constant rate. If you want this rate to increase again, you would have to add more enzyme because you need more enzymes to break down the substrates. Two other factors that influence the rate of our reaction are temperature and pH. So let's do temperature. And then we'll do pH over here. So generally, as you increase temperature, things move faster, so you have more collisions. So you're gonna have a faster reaction rate. So let's draw our axes again. Let's just draw our axes for pH while we're here. All right, for both of these, your y-axis is going to be rate of reaction. Okay, and then for temperature, we're going to have temperature on our X. We're going to do it in degrees Celsius. pH, you're going to have your pH scale. So for temperature, and let's just kind of give some numerals here. We'll go 20 degrees, 40 degrees, 60 degrees. As you increase the temperature of your system, your rate of reaction is going to increase because we're going to have more collisions. So the substrates will be colliding with your enzymes more. That's going to increase your rate of reaction. At some point, though, it's going to quickly drop off. So we have what we call the optimal temperature. The peak right here is called the optimal temperature for enzymes. So this is the optimal temp, and it's different for every enzyme. The enzymes in our bodies function best at our body temperature, but like bacteria who are thermophilic, their enzymes will work best at really high temperatures. So this positive slope, the reason that we're increasing our rate of reaction here is because our molecules are moving faster. That's what temperature is a measure of. It's the average kinetic energy, right? So we have molecules moving faster, more collisions, more interactions between enzyme and substrate. The reason it drops off so quickly is because at some point you're gonna hit the temperature that causes your enzyme to unfold. And then when the enzyme unfolds, its active site will change shape and it can no longer bind to its substrate. So this is the point when you've reached denaturing. So our enzyme is denatured. This is why it's really important that if you're like working out in the sun or like you have practice and it's hot out and you start overheating and you get like heat stroke, the reason that people can die from heat stroke is because it's denaturing the enzymes required for metabolism. And so it's like literally shutting down their ability to regenerate ATP and do cell respiration. So you can die from that. Over here in pH, it's more of a bell curve. So let's just kind of put some values down here. 0, 1, 2, 3. This will be an acidic enzyme. But as your enzyme approaches its optimal pH, it becomes more efficient. And then as it removes or moves away from its optimal pH, it becomes less efficient. So this one, there's kind of like zones of efficiency. We still have our optimal pH here at the peak. And then kind of like as you move away from that optimal pH, you become less and less and less efficient. So we're changing the shape of our enzyme kind of all throughout this, and we're making our enzyme more or less effective. So those are like a few factors that can alter the rates of our reactions. Also, there are things that can inhibit your reactions. So we're going to next look at inhibitors. And inhibitors can be like a reason a lot of poisons and toxins are poisonous and toxic is because they cause your enzymes to fold differently. And so you can't carry out these normal metabolic reactions that you would. So in inhibitors, we have two types of inhibition. We have competitive inhibition and you have non-competitive inhibition. Both are turning off enzymes or they're rendering them non-functional. So let's start with our enzyme. So we'll have our enzyme here. Let's draw two of them. So for competitive, we're gonna have we'll just draw a regular shaped Pac-Man enzyme. Non-competitive, we're gonna modify it a little bit. We're gonna add a second binding site like so. So these are our enzymes. Put an E for enzyme, E for enzyme. And competitive inhibition and non-competitive inhibition utilize secondary molecules called cofactors. and the cofactors are going to inhibit the function of the enzyme. A cofactor is another molecule. It could be an organic molecule, then you call it a coenzyme, or it could be like a mineral or a vitamin like zinc or iron, and they'll bond to the enzyme. So the cofactors are the things that are causing the inhibition. So with competitive inhibition, the cofactor is shaped in such a way that it is also able to bind with the active site. So this is my cofactor. And then let's draw my reactant, and they're going to be similarly shaped. This is my substrate. And it's called competitive inhibition because the cofactor is competing with the substrate for the active site. Because the cofactor can also bind to the active site. If it binds here, what ends up happening is it will block the substrate from binding. So we have this blocking. So the cofactors will bind to the active sites, and then our substrates cannot bind because their space is taken and they're blocked from binding. Over here with non-competitive, the cofactor will actually bind to a different part of the enzyme. But if you remember, every time you bond something to a protein, it's going to change shape. So when the cofactor binds, it changes the shape of the active site. So our active site will change shape. And now we don't have the lock and key anymore. So our active site changed shape, and now our substrate can't bind anymore. So we're just gonna draw like our little substrate. We'll draw an arrow, and then we'll just draw an X to block it. So we're blocking again. It's not really blocked. It just can't bind. They don't have an affinity to bind anymore because the active site was changed. So these are kind of like molecules that they naturally occur in our body, and then we ingest them in our diet, but it helps us regulate the function of enzymes. But also like poisons and toxins, if we ingest that in high amounts, then we can inhibit high amounts of enzymes, and then that can cause issues that could lead to death. One of these is reversible and one of these is not. If you have non-competitive inhibition, it's generally non-reversible or irreversible because you cannot remove the cofactor because it's on a site other than the active site. So non-competitive inhibition is typically permanent. Competitive inhibition can be reversed because they're competing for the same site. The substrate can actually dislodge cofactors. They're going for the same place. So if there's a cofactor here and a substrate comes to bind, it can dislodge the cofactor, and then it can bind, and then the chemical reaction will run. That can't happen here because your cofactor is binding to a whole different spot. So the substrate's never going to interact over here to dislodge because it's always just trying to bond right here. So these ones on competitive, they can actually be reversed. And the way to reverse these is just to increase your substrate concentration. If I have more substrate coming in, I have more chances of dislodging these cofactors and then running my reaction again. So it can be reversed by increasing our substrate concentration. Right? Because we're going to dislodge our cofactor. Because substrate can dislodge cofactor. So when you have a competitive inhibitor, as substrate increases, the rate of the reaction will actually increase because you're dislodging your cofactor. But with non-competitive, the rate of the reaction won't really change, even if you increase substrate, simply because you cannot reactivate these enzymes when you have a cofactor. It'll happen just at like a really, really, really low rate compared to competitive inhibitors. All right, last thing. This is a long video. We're gonna talk about how to activate and inhibit enzymes in different ways. This is gonna be called enzyme regulation. the key to like your body and all these chemical reactions is your body just like really wants control of everything. You kind of like learned that with signal transduction pathways. Like, why are there so many steps? Because we want more control. The more control you have, the more easily it is to maintain homeostasis and keep your body at a set point. So what we're going to talk about with enzyme regulation is how to control the activation and inactivation or inhibition. We'll say inactivation of enzymes. So the first type is called allosteric, well, there's one type, sorry. It's called allosteric regulation. The word allosteric means other site. So allosteric regulation is enzyme control by utilizing a site other than the active site. So we're going to control the active site by utilizing an allosteric site. And the word allosteric means other. So we're going to be using a site other than the active site. We've already kind of looked at allosteric regulation with non-competitive inhibition. The difference is both of these, the cofactors will only inhibit your enzyme, and then the lack of the cofactor activates your enzyme. In allosteric regulation, your body is secreting activators and inhibitors. So there's always going to be something bound to the enzyme. It'll just either be activating your enzyme or inhibiting your enzyme. And typically with allosteric regulation, you're going to have quaternary structure enzymes. So we're going to have a complex. So here's one tertiary enzyme. Here's a second tertiary enzyme. Third, fourth. So this is a quaternary structure protein. So we'll say quaternary enzyme. And it's made up of 4 subunits. So we have some different sites. These parts we drew here, like inside the little horseshoe, those are our active sites. So that's where our substrate will bind. And then these spaces in between our subunits, these are our allosteric sites. So substrate won't bind there, but regulators will. So we're going to utilize these molecules and they'll be similarly shaped. The thing that causes the enzyme to either be activated or inhibited is slight differences in the shape of the little molecule. Because if the molecule is shaped slightly different, then that will cause your enzyme to slightly change its shape. So we're going to have 2 little molecules that are just slightly different. One will be an activator. One would be an inhibitor. So depending on which one of these binds to your allosteric site, so they're going to bind here to the allosteric site. So it would look like this. You'll have your little lock and key, and it'll either have, like I drew, the little rounded top or the pointy tops. Like this would be an activator. When they bind, what activators do is they stabilize the active sites in the active form. Stabilize active sites in active form. Meaning they maintain their shape so that they're readily available to bind with substrates. What an inhibitor does, so if the inhibitor were to bind here instead, is it would stabilize your enzyme in its inactive form. So stabilize the active sites in their inactive form. So now none of these enzymes can regulate or cause a chemical reaction to happen faster, okay? And it only takes one, so you can have one bind and it stabilizes all of them in either the active or the inactive state. The way that you kind of toggle between activators and inhibitors is your body, to maintain homeostasis, the response will be, let's release some molecules that'll activate. So if you have a higher concentration of activators, you have most of those enzymes active. If your body stops producing activators but increases the production of inhibitors, then most of those enzymes will be inhibited. So we're regulating and maintaining homeostasis, so like production of a product, by activating or inactivating our enzyme. The last thing we're going to talk about is there's a specific type of allosteric regulation, and it's called cooperativity. So we're going to kind of indent a little. And what cooperativity is it's when enzymes in a complex cooperate. So you're gonna have, once again, a complex of enzymes. Let's draw 4 enzymes together. Let's give them a fun shape. So this is another quaternary structure enzyme. We have 1, 2, 3, 4 active sites. This is the inactive form. So none of them are binding. And you can actually cause all of them to become active by the presence of a substrate at one of them. So let's just draw one of them for now. So if one of them has a substrate bound, it causes it to activate. It also causes all the other 3 to activate as well. So you only need 1 substrate per enzyme complex to activate and stabilize all of them into their active form. So now we're in our active form. So they kind of all cooperate together, okay? So let's just flesh it out. The substrate binds to 1 enzyme. So say 1 active site. And then because they all cooperate together, they're all bound together, that stabilizes all others, so it's underlined all others, into active form. Right? What this does is it's going to amplify your response in the presence of a substrate. So the presence of this substrate causes all 3 of these to also activate. So now all 3 of them can also bind a substrate and run the reaction. So we're amplifying or increasing our reaction rate in order to amplify our response time. So the purpose of this is it amplifies our response. Of enzymes to substrates. Typically, your body uses cooperativity when you need to have a really fast response time to something. So if our body needs to create a product in a really short amount of time, those enzymes are typically quaternary structure, and they're all bound in such a way that changing the shape of one changes the shape of all, so that we can have a faster response time. And then we can also regulate them with our activators and inhibitors. So it's just like more ways for our body to have control of all the reactions we carry out. Okay, that was a really long video. If you need to watch parts of it again, go back and watch parts of it. Finish up your virtual lab. The SIRS will be mostly focused on this, so like rates of reactions, why they occur faster or slower. And then make sure you do those practice FRQs on Thursday, because as you know, the new AP test is just FRQs. So we're going to do a lot of FRQ practice, and then I'll post a key in the coming days. All right, I'll talk to you guys later. Bye.